Hello. Hi, I'm Gobi, and today I'll be talking about Sensemaking professional JavaScript. The question is, how can we help intermediate developers become experts? Today, I'll be talking about what distinguishes a professional from an intermediate developer, and then how we can transition those intermediate developers to becoming professionals. So I actually asked a bunch of developers who are professionals, what is it that distinguishes an intermediate developer from a professional? And they had mentioned advanced syntax, language paradigms, and regular expressions are things that could be distinguishing features. But we have tutorials that help novices achieve that, and we have HCI literature on things like tutorons that help novices achieve these set of skills and knowledge. Experts also mentioned logistics, just knowing how to use source control and Unix, package management, internet concepts, DevOps and continuous integration, logging, server setup. These are all rich tools that professionals need to know. But the thing is, even for this set of knowledge, it's quite effective to just use tutorials, and continuous integration setup is pretty basic after that, and it often enforces these type of good practices. So there's nothing really complicated to achieve here. Professionals went on to say it's important to know best practices for writing clean, maintainable, scalable, and secure code in order to be considered a professional. But for this, we have continuous integration and we have linting systems. And there's even HCI literature about an ability to automatically detect design, rule satisfaction, and best practices in code and style guide satisfaction. And this literature includes papers like active documentation. Finally, there's knowing how to Google search and search documentation in Stack Overflow. But increasingly, developers are becoming part of Slack communities of other developers who are more senior, as well as looking at Stack Overflow in more strategic ways. And Stack Overflow itself has better affordances for searching than when it started. So there is a considerable amount of support in this space as well to help people search and look at documentation in more effective ways. So it seems like the last bottleneck is really knowing architecture and design patterns. And this is something that almost every developer that I talked to who is a professional stated is something that novices need to learn, for which there aren't easy ways to learn right now. Consider Rodora. Rodora is a psych major at the University of Hawaii, and she wants to move into computer science because that's where the jobs are, and she wants to build sites like her favorite site, Reddit, and get a software engineering job. But the thing is that online courses cover introductory CS concepts and theory. They don't really cover what she needs to learn, which is software architecture and design patterns. Books and blogs sometimes do teach software architectures and design patterns, but she finds them too theoretical and not applicable to the projects that she's working on. And finally, she starts to realize that the best way to learn is actually to look at professional source code and start delving into professional source code. And there's a lot of HCI literature, in fact, 15 previous works I've identified that say this as well, that the best way to learn these types of patterns is to look at professional examples. But the way that people like Rodora look at professional examples is often through debugging tools like Chrome Dev Tools. And we have evidence of that. But that process of looking at professional code, either by reading it on GitHub or through debugging tools, it is confusing and has serious obstacles. Those obstacles include things like seeing relationships, asynchronous relationships in particular, but also just seeing patterns across a code base that are not all in one part of one file. So some of the contribution of my work that I'm going to talk about is creating alternative methods to debugging tools to help learners learn from professional examples, specifically learn how features are built, and these are features with complex underlying architectures. We know that the learning from professional examples is a great way to learn, and we know that people are using debugging tools right now, so and they're not fully effective. So we have a clear niche of where we can make a contribution. So some of the contributions that I have made so far this quarter is I've profiled the knowledge and skills required to transition an intermediate developer into being a professional. I've identified this bottleneck, which I described as architecture and design patterns, where existing solutions fail. And for this particular presentation and for this particular paper that I'm working towards, I'm going to be focusing even more specifically on asynchronous patterns and asynchronous architectures within JavaScript. And this quarter, I also design argued why developers should use graphical tools on professional examples, as well as some of the some of the improvements that we could make over existing graphical tools and existing tools that help with learning from sense-making professional examples, and I design argue for those improvements as well. I went ahead and profiled professional examples as well this quarter that have underlying patterns that are complex enough that we want learners to study them. And I identified fixes to these existing graphical tools to overcome existing obstacles towards learning how complex features are implemented and work in professional examples. So I want to get into some of these improvements, but first let's look at what are the outcomes we want. For Isopleth, outcomes of the existing tool were to understand asynchronous and synchronous control flow between code components and the order of execution of events and functions. It was also to understand complex relationships, both asynchronous and synchronous, between functions. For example, listenerception is a concept where one asynchronous callback binds another. But I found that after doing a number of studies in spring and summer and this quarter as well, some pilots this quarter, I found that Isopleth users still suffer from some obstacles towards those outcomes. They suffer from overwhelming amounts of code and nodes in the Isopleth call graph, minified code, not being able to have a visual mapping between JavaScript code and visual effects on the web page, unreasonable and confusing node labels, imprecise temporal access. So we know that Isopleth's nodes are arranged in a temporal order, but that sort of annotation of what point in time exactly am I looking at is not clear, and only the top level nodes follow the temporal order. And finally, there's this notion of facet color overriding, where a particular node may match multiple facets like DOM and AJAX, but the overriding behavior makes it hard to identify relevant nodes to a particular feature, especially when you're looking at the whole graph view. And you want to know that this node did 1, 2, and 3, and this node did these other two things. So this node had DOM, AJAX, and setup, and this one had mouse and DOM as well. And you want to know all those pieces of information at one time to be able to draw connections between those two moving components. So what I propose are a few design arguments for improvements that we should make to Isopleth, and why we should do them. So first of all, I think we should make the node labels more clear and simple. We should call things click event and click callback, so it's easier for novices to understand them rather than some of these more complex things that we see in Isopleth right now, which I have laid out on the slide. By having these simpler node labels, there's less of a need for learners to need to interpret the labels, and if they can just read them for what they are, that'll let them focus more on the architectural patterns present within the example. I think we need to hide the cluttering nodes that show nodes that touch purple arrows specifically. So we should show a node essentially if it's a top level call, or if it connects to a purple arrow and connects to other nodes across the call graph. Otherwise, we should not show it. And this will make us make sure that we have a reasonable number of nodes. All the nodes that we're showing are connected to important relationships, and learners will have an easier starting place, and they won't frantically jump from one part of the code to another, focusing on irrelevant code, and instead of opening up intriguing relationships, just getting lost in ones that might not be important. And it'll also create a more demand pull type of learning, which will help them discover what they need to discover on a need basis. So some of the examples were, we might just show a call graph that says load data, scroll, hover, and mouse leave for the Nat Geo example, rather than all these different nodes below. But learners can open up the call graphs and see the important function calls that happen underneath each of these main top-level calls. Now, we won't hide, however, important asynchronous relationships present in the graph. So if there was a child of this first node that had a purple arrow to this last node here, we wouldn't hide that child down there, or the purple arrow for that matter. So the final sort of change I want to do is I want to have multi-colored dots. So I want each node to have an annotation for each facet it matches, so that I can identify quickly that there's one node that matches both DOM and Ajax, and another node that matches mouse, DOM, and setup. Sorry, mouse, DOM, and Ajax. So by having these multicolored dots on each node, learners can easily see the different roles of individual components. And then by seeing the multiple roles of individual components, they can clearly understand how those different components work together to implement a feature in ways that would be impossible if they could only see one of the facet colors and the rest were overridden. So the overall design argument I'm proposing is to provide a clean, abridged timeline call graph that highlights important asynchronous and synchronous relationships, has human-readable node labels, and that has clear annotations of which nodes of what facets each node matches, so that we don't have to guess which facets are overridden. And what would be an even bigger plus is if we had mappings between each of the function calls or each of the nodes and the corresponding page screenshots at that point in time. So we can really see that these are function calls and they changed how the page looked at that time. These features will help novices overcome overwhelming, minified, contextless, and disorganized code structures that are sort of the plight of ISOPLET 1.0, and they will help create a better ISOPLET 2.0. They'll help them in ISOPLET 2.0, which has these fixes, visualize asynchronous and synchronous relationships and data flow. It'll help them understand how complex features with sophisticating underlying architectures are implemented in practice in JavaScript. So overall, this solution is novel and unique from ISOPLET 1.0 because it addresses the tool's overwhelming, minified, contextless, and disorganized code structures and node graphs. It leverages a cleaner graphical representation with non-overriding facet coloring, readable node labels to help novices see complex features with sophisticated underlying architectures. It will work because ISOPLET worked to an extent, but failed due to serious limitations. These improvements address the limitations and extend the tool to be more useful for understanding how complex features are architected and coded. So it should work better than ISOPLET does. And we think that it addresses the major obstacles, so it should work quite effectively in general. The purpose of our study will be to understand, do graphical tools like ISOPLET enable learners to effectively sense-make JavaScript applications with sophisticated underlying architectures, particularly asynchronous ones? And we want to answer also, do graphical tools like ISOPLET allow learners to understand asynchronous and synchronous relationships, data flow, and coordinating components better than the status quo, which is quite popular, of browser debugging tools? And we have evidence that the status quo is the popular way of viewing source code right now. Now, specific study questions will be, do graphical tools allow learners to understand async and sync relationships, data flow, and coordinating components? Does the bridge timeline call graph lead learners to demand pull, explore coordinating events and relationships that occur over the course of an interaction, rather than just, being overwhelmed immediately by seeing everything all at once? Do the human readable node labels and unminified code paints help learners interface with professional code components without confusion? Do the multicolored dots to tag each node with the facets it matches overcome issues of facet overriding and lead to better comprehension of the roles different coordinating components play in an overall coordination? Now, in our study, we recruit 10 users, graphical, and 10 users for debugging tools. And we might have a third condition, which might be Isoplet 1.0. Now, we'll have them go through an introduction to the whole study and a participant check against, a cheat sheet of terms that they should know before coming in, like asynchronous, callback, things like that. Then they'll go through a training for whatever tool they're learning to use. They'll use the tool on a professional example. And then finally, we'll have them, one, describe the architecture of the example, then make a diagram of it, and then answer measures that are specific to different things that we're asking them about in terms of the architecture. And the reason why we start with describing an architecture is more to Matt's point about, if you're just having them do a diagram, that might be a biased thing to ask them, considering that they had a much more graphical representation in the Isoplet condition than in the debugging tool condition. But if we start with a description and we find that the descriptions that they're coming up with are more accurate in the graphical tool condition than in the debugging condition, we don't run into that type of bias, making our study more robust. We will have measures that are tiered. So first, we will ask them to describe the architecture, then draw a diagram, and then finally answer questions about specific features of an example. What we mean, but even this part will be tiered. For instance, we'll first ask them to describe each event listened for and the role of each callback, but then we might ask them more specific things like, did you find that a callback registering or unregistering another event listener happened? And yes or no, and if you did, can you describe a little bit more about that? So we might prompt them more specifically later on in a measure. Finally, we'll just ask them about how they figured out what they figured out using the tool that they were given and what strategies they used. So we'll have quite a bit of evidence. We'll have a talk aloud where we'll prompt them every minute they're silent to say what they're thinking during the tool use. And then afterwards, we have measures that ask them what they know. And during the measures also, we'll ask them, how did you figure out what you figured out using the tool? So I'm going to present results that I got from prior studies because I haven't run this study that I described right now. And basically what I did in prior studies was I had similar sort of measures and a similar sort of study procedure, but I didn't have the Isoplet tool improvements. And so what I found from my past study was that Isoplet helped with outcomes with underlying asynchronous architectures, but not with other types of outcomes. So what I think we can learn from that past study is that we should focus more on architectures that have underlying asynchronous patterns. And so choosing examples like that is important. The other thing I noticed in the study that I performed previously was that the mechanism of how people use the tool was effective. So we found here that when we graded how people use the tool, if they use the tool well, they tended to do well on diagrams. And when they use the tool poorly, they tended to do poorly on diagrams. And so they use the tool well for things like outcomes that involved asynchronous architecture, and that ended up resulting in them scoring well on diagrams. And they used the tool poorly when they were dealing with outcomes that didn't have to do with asynchronous architectures, and that ended up having them do poorly. That ended up resulting in them doing poorly on the actual diagrams. So what we found is that these mechanisms sort of aligned with our diagram scores, and we hope that they'll align with our measures in the next study as well. One of the things is that when we did measures, they had some jargon in them. So we simplified the measures this time around, and we plan to run a study with simplified measures with simplified language. And we believe that should resolve the issue that we had with measures of the previous study. So overall, the study procedure included a qualifying diagnostic test and a recruiting email, and it included a procedure for graphical tools and debugging tools, and then a mechanism that was measured during the tool use, a diagram that included a prompt and a rubric, and then measures themselves that also we included a rubric of how to grade them. So we get a fairly good set of data to evaluate how people are performing on graphical and debugging tools to understand professional examples. So we were able to show that graphical tools are superior on examples with rich asynchronous architectures. By knowing this, we know that we should focus on a rich set of examples within this niche of asynchronous architectures for the purposes of this paper. We can expand to highlighting other types of architectures in our next work. So that presents a limitation of the current work that we're working towards, is that we're going to be limited to asynchronous architectures. I'm concerned that reviewers will critique debugging tools and Chrome Dev tools as a control, because that's not the intent of control. That's not the intent of Chrome Dev tools. The intent of Chrome Dev tools is not necessarily to help learners learn from professional examples. So we'll need a justification. We'll need some evidence that says that, learning from professional examples is established in the literature as an effective way to learn things like design patterns. We'll need justification to say that people are using Chrome Dev tools and debugging tools more than any other tool to learn these design patterns from professional examples, or at least to learn things from professional examples. But even despite doing that, we might need to have another condition. So we might need to have an ISOPLIT 1.0 condition, a Chrome Dev tools debugging techniques type of condition, and ISOPLIT 2.0 graphical tool condition. So we'll need to figure that part out. Now, next steps. And so my first next step is to fix our tool as per the obstacles and design arguments presented in this presentation. So a lot of tech work. Then I need to justify debugging tools and Chrome Dev tools as a control. And I need to justify that people use Chrome Dev tools and debugging tools to study pro source code right now, and also that studying pro source code is important. And it's an effective way to learn to becoming a professional. Learn how to become a professional. And then what I need to do is I need to compile a rich set of examples, maybe 10 or more, of asynchronous architectures, preferably with unminified code, or design a sort of extension or bot that can search and detect for such sites. And I also need to find non-asynchronous architectures to show our limitation that we're constrained with two asynchronous architectures within this work. We need to show that our technique doesn't work on non-async architectures. Then after doing all that, I'll need to show that ISOPLIT 2.0 for asynchronous architectures is effective, and it is better than widely used, I'll need a citation for that, status quo debugging tools. And I would need to argue that it's better than some of the previous 15 learn from professional examples types of works that we find in HCI literature. Now, once that paper is done, then we can maybe go on to the Siegel project of making an ISOPLIT 3.0 that highlights all the architectures and design patterns, not just async ones, not just make it easier to discover the async ones, but highlight all the architectures and design patterns. And we'll need to show that ISOPLIT 3.0 is more effective than debugging tools, iSplit 2.0, some of the other 15 previous works, and learning from examples. And once we do that, that might be another paper. Then we could probably do this in the wild. So we could do iSplit 3.0, which is this highlighting project, highlighting architectures project in the wild. That might be another paper. Then there are some other ideas where you could integrate in scaffolded exercises, integrate in knowledge maps. That might be another couple of papers. And then we'll have a good sense of where Rail is and what Rail is able to do, and hopefully it'll be effective. And at that stage, we could probably do each of those things, scaffolded and knowledge maps, in the wild. And then I'm hoping that in the course of the PhD, I can at some point, or even if it's after the PhD, I can at some point publish the work I have about how we incentivize intermediate developers towards completing the required set of learnings towards becoming a professional. So doing things like scaffolded exercises and iSplit 3.0 knowledge maps, but also learning things just from tutorials. And so I did some work on financial incentives in that space. I hope to get to that at some point, and then doing all that in the wild. I run a community of around 450 developers around the world, and I can run some experiments on that. And I hope towards the end of my PhD, or if I pursue a postdoc, I'll get to collaborate with some of the other people in this field, and publish more with other people as well, and also do research that can tap into the community of developers that I've built. So this is an overall sort of plan I have. There are a few trade-offs because I'm running this community of developers. I'm very much interested in this specific type of research, but this specific type of research requires a lot of system building. So it can be slower in terms of research progress than just doing studies. But hopefully the research will transfer into practice, and I can have people in the wild use some of these tools and actually transition from intermediate level to professional and work for real clients or get real jobs. So I'm very excited about how my PhD is focused on Rail right now, how I can leverage it in the community of developers I've built, sort of the trajectory of doing things in a small scale and then in the wild, and integrating all the different projects within Rail into the wild. And I think that this trajectory is quite vague right now and high level, but hopefully by doing iSplit 2.0 well, we'll have a good set of groundwork towards achieving some of these other milestones that I've touched upon. Thank you.